Hello, this is Schweitzer in a little short video on what is a buffer and how do I calculate the pH of a buffer. For the most part, the majority of this topic has already been covered in previous videos, but we'll sort of isolate it and discuss it from the idea of a buffer. A buffer obviously is something that can resist change in pH. So if you were to chart this out on a titration, let's take for example our HF acid. We'll put pH on the side here and total moles of hydroxide added. So we're talking about a titration system, maybe with a burette, and we're going to drop in some hydroxide and neutralize our acid. The equation is going to be HF plus H2O yields H3O plus and then F negative. The side reaction is going to be H3O plus the OH that I add, yielding H2O. So I'm going to add a hydroxide here and consume this H plus ion, and therefore causing the reaction to shift in that direction. If you combine these two reactions for what might be happening, this is truly what's happening, but I would say we could maybe think of it like as HF plus OH negative yields F negative plus water. So every time you add a hydroxide, you kick one of these guys over to that point. Alright, so that was kind of discussed. If you were to track it, you'd see that if this is 7, then it's going to start relatively acidic, and as I add and record my data points, you'll see it slowly creep up until it reaches its equivalency point, and then it's going to just really shoot up like that. It's buffering in this area. As long as there is some acid left, then it will stay in this general buffer zone. Usually if this is a, let's say 3, it would buffer to 2 to 4 range. 1 pH unit in either direction is considered its general buffer zone. So kind of recap this a little bit. A buffer is any time you have an acid and you have its conjugate base present. Usually it'd be described as an acid and its salt. Calculating the pH of this thing, any buffer solution, it works just like a lot of our other calculations. If I were to have a buffer solution of HF, okay, and let's go plus H2O yields H3O plus and F negative. Now keep in mind, there is a reverse reaction here where this guy is basic. It is a weak base. It's a weak acid. So in a solution, initially we have to have both of these present. This could be 0.1 molar and this could be 0.05 molar. In fact, let's make it a little differently. Let's go like this. Let's go erase this, and let's say this is going to be, didn't quite erase this, and rather than making it smaller, let's make it bigger, 0.5 molar. We even have a higher concentration of base than we do acid. Let's see where it turns out acidic wise. So stoic ratio ending, water will not play a role because it doesn't have a changing concentration. We're tracking concentrations here. This is nothing to begin with. Minus x plus x plus x. This is going to be 0.1 minus x, and 0.5 minus x. Plug these values into my equivalent expression, which is going to be Ka of the HF, which is 6.6 e to the negative 4th, equals the products, the concentration of H3O plus, concentration of F negative, over the concentration of the HF. And plug your values in. I'll use my shortcut rule here and here. So it's going to be x times 0.5 over 0.1. Grabbing a calculator, solving for x. 6.6 e to the negative fourth times 0.1 divided by 0.5, and I get, in this case, X equals the concentration of the H plus ions at being let's go 1.32 e to the negative, squeeze in there, fourth. Okay, 1.32 e to the negative fourth, that's molarity. Now that would be considered concentration of H plus ions. Okay, from that point I would take the negative log of that value, 1.32 e to the negative fourth. This will give me my pH of that solution. Now, I automatically know that this is going to be an acidic solution because the T-retard point, the middle of the road, is 1.0 e to the negative 7. That's neutral. So my H plus ion concentration has gone up from there, and therefore my hydroxide ion has to have gone down. And the negative log of that answer is 3.87 is my pH. 3.87. Alright? Definitely, even though I have a much higher concentration of base, my acid went out because of the larger Ka value of the acid. What is a pKa and what is a pKb? Well, for the most part, I find that I can do all of my mathematics, everything, without even having to utilize pKa or pKb. So, not a huge fan of it, but essentially, for let's say, a concentration of an H plus ions, let's say is 1.0 e to the negative third. So this thing would have a pH that is equaling 3. So this is taking this concentration and putting it into a little bit of a scale, 0 to 14, and kind of letting you know where this thing is on the scale of acids to bases. Okay, this is acidic, this is basic. Well, a pKa does a very similar item. Now for HF, the Ka is equal to 6.6 e to the negative fourth. Okay, therefore the pKa is equal to the negative log of 6.6 e to the negative fourth. And this is meaning that it is going to be 3.18. Okay, now like I said, every acid reacts with water to produce H3O plus ion and F negative ion. So there are two factors. One is this K, how much it moves to products, and the other is the initial amount of it that you have. Well, it turns out that this K value is quite representative of what you're going to get. And therefore the pKa does tell us roughly where this thing is going to land. And in fact, on my last one I just did, it landed at 3.7, even though I have more of my base than I do acid. Okay, so pKa can be useful for estimating where you think this buffer zone is going to be falling. I'll move up here a little bit. Okay, this buffer zone is going to be right around 3-ish, give or take a little bit, but it's right there. It gives a good indication of where your acid will be. Now, another example of where I might utilize a pK is in the idea of when I have an acid, let's say HF plus H2O yields F negative plus H3O plus. If the concentration of my acid and its conjugate base are the same, then you'll find that the Ka equals the concentration of F negative.
Will the following students please come to the high school office? Cameron Luker.
You'll find that F negative, we have H3O plus ions. Let me grab this here. Interrupted there for a second. And H3O plus ions, and then HF concentration. If these are the same, they cancel, and your Ka will equal your H3O plus ion concentration. That's a shortcut you should know. But then, ideally, if they're equal, then your pKa, if you negative log this thing, and you negative log this thing, then your pK equals your pH. So, if they're equal, then your pKa will equal the pH of the solution. Okay, so it's a little bit of a shortcut that, fortunately or unfortunately, is used quite a lot. A lot. It's there once in a while. Thank you.